We are finally here. We are now going to start some calculus topics. The first topic that we're going to be working with in calculus is limits. I'm sure if you watched Mean Girls in the past, you've heard or seen memes about the limit does not exist. Well, we're finally get to see and acknowledge if a limit exists or not. All right, so this is one of the first major concepts we're going to cover. This is going to be a week 1 of 2 weeks of limits. We are going to work with some more advanced stuff next week, a more algebraic approach. But this first week is going to be more numerically and more graphically. Okay, so we're looking at a very simple problem here. It says you're given 24 inches of wire, and you're asked to form a rectangle whose area is as large as possible. Determine the dimensions of the rectangle that would produce a maximum area. Okay, so if we kind of draw the situation, this is more of a polynomial problem. Okay, so we have a rectangle. I know if I use W here, the same thing is going to be on the opposite side. Now this side here is going to be 12 minus W. Same thing with the other side, right? The reason why I choose 12 minus W is because if I use 24, keep in mind that you're working with two sides that have to be the same, right? So a lot of you would do something like, if this was W, this would be 24 minus 2W, but remember you're going to have two of those, so I get 2 times 12 minus W, so that gives me the length of 12 minus W here, 12 minus W there. So that's kind of where I'm getting that from, if you're just a little bit unsure on where you got the 12 minus W. Okay, so we're talking about areas. How do you find the area of a rectangle? Okay, well the area of a rectangle is just going to be length times width, so here's your function, right? So you want to find a maximum area. Now the word maximum, when we work with quadratics, just represents we want to find the vertex. Now since this is already in factored form, we can just go ahead and do that. So we get one of our zeros is W, the other 0 is 12. So we have a 0 at 0 and 12, but we're looking for the maximum, and the maximum is going to be at the halfway point between that. So the maximum volume is going to be, or the maximum length of the wire is going to be 6. And if it is 6, then the maximum area we're going to have is going to be 6 times 12 minus 6, which is 36. Okay? All right, so this kind of information that we're finding is good in the application sense, right? If we're looking to determine a rectangle that's going to form a maximum area, let's say you want, your cattle herd or anything or something like that, and you want to find the maximum area for your cows to kind of just roam around in your farm. You want to figure out what's the best possible way of doing that, but using a certain amount of wire, right? So to do that, you would kind of make a square here, a 6 by 6 square, and that'll give you an area of 36 square feet, and that's the most area that you'll have in terms of, your farmland, or whatever case you're kind of working with, right? So this is kind of like a problem that you would do normally in Algebra 2, all right? But we kind of want to take this approach, and we want to look at it in terms of as a setup to limits and understanding what are we actually doing here, what are we approaching, right? So I want to just kind of quickly show you guys what this graph would look like, right? It's going to be a quick rough sketch. So I know that this is 12. We're going to make a 6 marker here. This is 0. We're going to go up to 36. So there's my vertex of my graph, and it's parabolic. Right? So what I want you guys to kind of understand here is understanding behavior of a function as you're approaching a value on that function, right? So if we look here and we're trying to approach the maximum value from the right-hand side, okay, notice that these y values are getting closer and closer to the value of 36 as we approach 6, right? And the same thing occurs here. As we travel, okay, from 0 to positive 6 on the x-coordinate, the y values are getting closer and closer to this 36. Now, as you approach it from both sides are kind of in agreement that the value will approach this 36. Now, it is not necessary for the function to to exist at 6, but understanding how the behavior of the function is being approached from both sides of the graph is very, very important. That's why, a lot of times in pre-calculus, when we start off, we're just recognizing graphs, understanding graphs, different kinds of graphs, everything from polynomials to trigonometry, because you need to understand how graph behavior works for some of these concepts in calculus. Okay, so let's actually get into it. What is a limit? The definition of a limit. Okay, so it says if a function becomes arbitrarily close to a unique number L, okay, it's just a particular number L, as x approaches c from either side, the limit of the function as x approaches c is L, and this is written as the limit of the function as x approaches c equals L. Okay, so this is the notation we're kind of going to see a lot of. Okay, now in our problem before, right, we were looking at the limit as x approached 6 of our function, and our function in that case was, it's going to be in terms of x, so x times 12 minus x, okay, and we found that limit to be equal to 6. Okay, so again, what I want you to understand is that this was our given function. Okay, we were approaching the value of 6 because we identified that 6 was the x value that we wanted to kind of find the value for. Now, as we approach the function from both sides, we noticed that as we approach this 6 value, we got closer and closer to this 36 value. So that comes again from the image of the parabola here, okay, where as we got closer to this 6 value from both sides, the value went to 36. Okay, so in a sense, it was kind of like we substituted the 6 here and we got 36 for our function. Okay, but now substitution is something that doesn't always work, but again, it just all depends on how we approach the problem. All right, so let's estimate a limit numerically. Okay, so we're going to use a table to estimate the limit numerically. Now, remember, when I told you we are looking for what is the value of the function as we get closer and closer to 2, right? Now, again, this notation, the x approaching 2, represents, okay, we have to get close to the 2 from both sides, all right? So what I want us to do here is I actually want us to create a table, okay? So we're going to go x and then the function, okay? So our 2 is going to be in the middle. And I'm going to put a question mark there because we want to get as close as possible to this 2. All right, so a number that's really, really close to 2, that's less than 2, is 1.999. A number not as close as 1.99 is 1.99. And a number that's not as close as 1.99 is 1.9. So basically, I'm starting at a 10th distance from 2, then a 100th distance, a 10th distance, a 100th distance, a 1000th distance, right? If we wanted to, we could go 10,000th distance, but this is pretty good because you're pretty much going to get an accurate representation, right? When we round to 3 decimal places, you kind of get as close as possible as you want to. And then in the other direction, we're going to go 2.001 because that is 1,000th close to the 2. And then we're going to go 2.001. Sorry, not 0.001. And then we're going to do 2.1. So again, we're going to start at a 10th distance and work our way as close as possible to the 2. Okay, now the reason why we want to do this is we want to see if the behavior of the function is approaching a certain value. Okay, regardless if when we plug in that value, we get that value or not. All right, so these again are all positive. I just used this little marker here to kind of show you guys what I was talking about when I was talking about it. So let me see if I can erase this because they're all positive. Okay, all right, so what we're going to do here is we're going to brute force plug these in. All right, so we're going to go 3, and we're going to substitute the 1.9, and then we're going to subtract, we're going to close this and subtract 2. Okay, so I get 3.7. Okay, 3 times 1.9 minus 2. Now, what we're going to do is we're going to add an extra 9 here. So we get 3.97. Okay. And then we're going to add another 9 in here, and we're going to get 3.997. Okay, so what's the trend that looks like is happening on the left-hand side of 2? And again, when I talk about left-hand side of 2, okay, since our x-axis goes like this, if this is 2, then 1.9, all these values will be to the left of 2. So from the left-hand side of 2, what is happening? It looks like it's approaching a particular value. In my opinion, it looks like it's getting closer and closer to the number 4, right? So let's see what happens if we go in the other way. So instead of this 1.99, let's go ahead and put 2.1. All right, so I get 4.3. So now we're going to get closer. We're going to put 2.01. That's 4.03. And let's try 2.001, and we get 4.003. All right, so from both directions, all right, if you had to make a safe assumption, what would you say the limit of the function 3x minus 2 as x approaches 2 is going to equal? Well, it looks like just based on the pattern, okay, it looks like from both directions they're approaching the number 4, okay? So let's see if that is the case when we work with it graphically, okay? So on the next slide here, I have the graph. Here's our function, 3x minus 2. It's a line, okay? So we're going to look at the graph as it approaches 2, okay? So here's the 2 value, right? We want to see what's going to happen to the function as it approaches 2. So from the left-hand side, it looks like it is approaching the number 4, right? And then from the right-hand side, it looks like it's approaching the 4 as well. So the behavior of the graph as you're approaching the x value of 2 from the left-hand side and the right-hand side is 2. Okay, so therefore the limit exists and the limit is equal to 2. Let's look at our next example. All right, so here's one that's a little bit more complex. Again, we want to use a table to estimate it numerically and see if we can get a limit. So again, we want to use some values here. Now, this time we are approaching this function as it approaches 0. So 0 is going to be our middle number here. We're going to see what the limit is if it exists as it approaches 0. All right, so we're going to go negative 0.001, negative 0.01, negative 0.1. And we're going to go positive 0.001, 0.01, 0.1. All right, so these are the values you kind of want to use. Again, you want to get just a decimal place closer each and every time. Okay, and you want to be exactly to the right and exactly to the left of the number that you're working with. Okay, all right, so let's look at this function here. So let's kind of put the shell into the calculator here. All right, so we have x. So let's start with the topmost number here. So that's going to be negative 0.1 divided by, let's make sure this negative sign is in the numerator. Okay, and then we're going to have the square root. Looks like we're going to do negative 0.1, and then we're going to go plus 1. And then outside of that radical, we're going to go minus 1. So let me just make sure here, have everything going on. So I have x over the square root of x plus 1 minus 1. Okay, so now all I have to do is just change the values in the x position. All right, so here I get 1.948. Okay, so let's add in another 0 here in front of the 1. I get 1.99. Okay, and if I plug in one more 0, I get 1.999. All right, so on the left-hand behavior here, it looks like that it is getting very, very close to 2. Okay, but that's, again, just one hand side. We have to verify that the other side is doing the same behavior. All right, so let's take a look. We have 0.1, 0.1. So we have 2.0, 0.48. If I put in a 0 before the 1 here, let's see what happens there. I get 2.004. And then add another 0 in front of that 1. And I get 2.0004. Okay. All right. So looks a little obvious here. What is going to happen as you approach this value of 0? Well, the limit as the function approaches 0 is going to be equal to. Okay. Now let's look at it in the graphical interpretation, right? So here we have our function. Okay. So let's see what happens as you approach the function from the left and right hand side. So I'm going to go from the left hand side here. What value is it approaching at the x equals 0 mark? It looks like it's approaching the value of 2. And let's do it from the left hand side, from the right hand side here, excuse me. It looks like, again, it's approaching the same value. Now, I want you guys to pay close attention here to what this says. It says f is undefined at x equals 0. Okay, in this function, there is a hole, right? The reason why there is a hole, right, is if I substitute, if I substitute 0 into the function, which is the value we're kind of looking towards, what happens here? I get 0 over 1 minus 1. And that's 0 over 0, which is an indeterminate form, okay, which is undefined, okay? The function is undefined at this particular point, okay? So therefore, that function does not exist at this point. However, the limit still exists because the definition of the limit just states that as long as the behavior of the graph or the function is approaching a certain value from both sides of the function, then the limit exists. Okay, so this answer of 2 that we got is correct. Okay, this is correct, right? There is a limit to the function. However, this function does not exist at that value. But that does not have any bearing on identifying limits, right? And that's going to be very important later on once we start getting into some more difficult limits, okay? So the idea that the function needs to exist at that value has no bearing. That's why when I said substituting may or may not work, because sometimes substitution doesn't work because of cases like this where you have holes, or it's discontinuous, or you may have an asymptote, okay? So you have to be very, very careful and just identify the limit based on the rule. What's the behavior as the graph approaches from the left and from the right? Or in this case, since we're doing it numerically, what's happening with the function as we move left, as we get closer from the left-hand side and the right-hand side of the value we're trying to identify the limit. Okay, here's a polynomial one. We want to estimate what the limit's going to be. We are going to approach this function as it find the limit as it approaches 1. So here we go. We're going to have f of x. Again, if you want to start doing this on your own, you can. Just pause the video. So we're going to go 0.999, 0.99, 0.9. The other way, we're going to go 1.001, 1.01, 1.1. All right, so we're going to get closer and closer to this one. We're going to identify what the limit is going to be equal to. All right, so let's get this function into my calculator here. So we are going to have a fraction, and it's just going to be a polynomial. So I'm just trying to erase what we have here originally. Okay, so in the numerator, I'm going to have 0.9 to the third power. That's going to be minus 0.9 squared plus 0.9 minus 1. Again, I know this is a very tedious aspect of identifying limits, but this is the most basic approach to a limit that we can possibly have. All right, so you're going to plug in the 0.9 have. So we're going to 1.81. Okay, now let's add a 0, or let's add another 9. So we're going to add a 9 to each of these. I get 1.9801. All right, let's add another 9. So I get 1.998. So again, from the left-hand side here, it looks like it's going to get closer and closer to the value of 2. Now let's work in the other direction. So we're going to change all these bases we're going to start with 1.1. So let's change these bases. Again, I like using the Desmos calculator here because you can quickly edit your previous function without having to do much. Again, if you have a graphing calculator or something like that, you can also do the same thing. It's not too difficult. It's just whatever's more convenient, especially for some of this tedious work here. So for the first one, I got 2.21. Let's put a 0 in front of the ones here. All right, 2.0201. And one more 0 in the front. And we should have our limit here. All right, so we get 2.002. All right, so what number is it getting closer and closer and closer to as we push closer and closer to this one? Well, it looks like the limit of our function here as it approaches, as x approaches 1. Is going to be equal to the number 2. Okay, so here's our limit. Okay, so really quickly, if we substituted 1, what would we get? We would get f of 1 would actually be equal to 1 minus 1 plus 1 minus 1 over 1 minus 1. What do we get? We actually get 0 over 0 again. So again, it does not exist in the function, but the limit exists, and the limit is equal to 2. Let's look at the graph of this function. All right, so here we have this parabolic graph, except there is a hole at the function at x equals 1. It's undefined there, okay, and we already showed that it is undefined. All right, and keep in mind the reason why it's a parabola is because when we simplify this, or where we divide, the function is going to be a quadratic. It's going to be a quadratic drawn, and then it's going to have a hole. Because in a denominator, we have to avoid all values that's going to make our denominator equal to 0. Okay, so that's why it has a hole in this particular function. But again, just like we predicted, it doesn't exist at x equals 1, but it does approach what value? The value of 2. Okay, so the y value is still being approached. Again, it does not matter if the function exists at that value or not, but it does matter that the function approaches it from both sides of the function. Okay, let's use a graph to find the limit. All right, so let's find the limit of this function as x approaches 3, where f is defined as the following. All right, so let me just see. I do have the graph here. Okay, so really quickly, it is a piecewise function. What it's saying, and we can kind of quickly draw this, and we'll just look at the next slide to confirm. What it's saying is that the function is going to be equal to, but x cannot equal 3. So what that tells me is that my function, here's 2, is going to be a horizontal line, except at the x value of 3, there's going to be a hole. Okay, so there's my function. And then the second part of the piecewise function tells me that at x equals 3, y is 0. So basically what we have is we have a continuous horizontal line, okay, but then it has a point of discontinuity here, okay, so it's no longer continuous at that position. Instead, what we have is we have a point down here, so basically it's kind of like we removed the point from the function and just dropped it down to the 0 location at that particular case, right? Now, this function does exist everywhere. The domain is all real numbers. So it does exist everywhere, but let's see how the function, the idea of the limit is for this particular case, right? All right, so let's do this one numerically. So we have x, f of x. What number are we going to approach? If we wrote this in limit notation, we're doing the limit as x approaches 3 of the function. We're going to leave it as f of x because it is a piecewise. We're going to see exactly what this limit is equal to. So we're approaching 3, so we're going to go 2.9, 2.99, 2.999, 3, 3.001, 3.01, 3.1. All right, so let's identify what's happening with the function as x approaches 3. So at 2.99, what is the function equal to? Well, we have two options. We have 0 or 2. Now, it's probably going to be this one, okay, for almost all of them, because the only rule is what is happening at x equals 3. So this is going to be 2, 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 2, and 2. So based on the rule of a limit, okay, we are approaching what value this way? We're approaching the number 2. What are we approaching this way? We're also approaching the value of 2. So the limit of the function is going to be 2. Now, this is one where the function does exist here, okay, but that's not the purpose of the limit. The limit tells us to look at the behavior of the function as you go from the left-hand side and right-hand side as you approach the value. So as we approach this value and we get closer and closer to the value, we are approaching the number 2. The limit is equal to 2, even though the function is equal to 3. Okay, so the limit is actually 2 because we're just talking about the behavior as it approaches these values from both the left-hand and right-hand side. Okay, so comparing left-hand and right-hand behavior, all right, so we've been kind of doing that already. We've been showing what happens on the left-hand side and the right-hand side. We want to make sure that they kind of coexist to give us a limit. Now, we're going to look at cases where they may not coexist. So let's look at this example. So what we have here is the limit as x approaches 0 of the absolute value of x over x. So the function is provided here in the image. Okay, so let's look at the behavior from the left-hand side of 0 and the right-hand side of 0. So on the left-hand side of 0, this function would be approaching what from the left-hand side? The function looks like it's approaching -1. Okay, but what's happening as we approach it from the right-hand side? From the right-hand side, as we travel this way, it is approaching +1. Now, we all know that -1 does not equal +1. Because the behavior is not in agreement, okay? Because they do not agree, therefore, the limit does not exist. The behavior needs to be true on both sides of the function as you're approaching whatever x value they're telling us to approach. Because, excuse me, because the limit does not approach the same y value, the function does not exist. The limit does not exist for this particular function at x approaches 0. Okay, so for this one, the limit doesn't exist. All right, so there you go. There's your Mean Girls reference. All right, let's look at the existence of this limit. So the limit of 1 over x squared as x approaches 0. So here's a rational function, one of your typical rational functions. So we're looking at the limit as the x approaches 0. So let's kind of discuss what's happening here. So on the left-hand side, my function as it approaches 0 looks like it's approaching what value? Okay, now I don't see it really approaching a value. Instead, what's happening is it's approaching a big number here, the infinity idea, all right? On the right-hand side, as we go the graph approach 0, it is also approaching infinity, Okay, now this goes back to the definition. The limit L needs to be a unique number. Okay, now the limit in this function, you can kind of see that both sides are in somewhat of an agreement. They are approaching something that is going to be higher than what the image shows us, right? But we know based on the behavior here that the function is going to approach infinity, okay? Now, infinity is not a unique number, okay? A unique number is a number that we know to exist. Infinity is a concept that we are approaching this really large, quantity, but no one knows what this quantity is, what it looks like, okay? So because this function does not approach a number, a real number that we can grasp, that we hold, that we understand, therefore, okay, the limit does not exist, okay? And the reason it does not exist is because infinity cannot be bounded. We cannot close off infinity. We cannot stop infinity. Infinity is going to keep going. So for this one, unfortunately, even though both sides are kind of in agreement, the limit does not exist because of this idea that we cannot contain infinity at that particular location. All right, so anything that kind of deals with unbounded behavior is going to kind of have that idea behind it. Okay, then let's discuss the existence of this limit. Okay, so what's the limit of sine of 1 over x as x approaches 0? Okay, so what is happening here? Okay, so what I kind of want to show you, if we zoomed in really, really close, what's happening is this. The function's going up and down, up and down, up and down, an infinite number of times with basically no space in between the curves, okay? Now, what we call that is we call that an oscillating behavior. Okay, now the tricky part about this is that we know that the function is going to be contained between +1 and -1. The only problem is because it's oscillating so much near 0, we don't know exactly what's going to happen at 0. So we can't even calculate what's going to happen on the left and the right hand side here. It's kind of, there's no real way of understanding that. Even if you get really, really, really close with the table, you're still going to get too many fluctuations, so we don't know what the limit's going to be in certain oscillating behavior, just like you have here, okay? So again, here, the limit does not exist. Another reason being oscillating behavior. So there are 3 ways that we kind of talked about here, and their examples are listed here, in which the function or the limit of the function does not exist because one of these 3 conditions have to be true. So the first one is the one where both the left-hand side and the right-hand side are not in agreement. They need to be in agreement. They need to be approaching the same value. Keep in mind that C needs to be a value that we can grasp, that we can hold. It's a real number that's defined. Okay, so we need to understand that both sides of the function at this x location is approaching the same y value. 2, the function increases or decreases without bound. That's one like example 7 where we can't contain it. It's going to keep going on forever and ever. We don't know what the limit's going to be. We can't approach it. We can't stop it. So therefore, the function does not have a limit. And the third one is behavior that usually happens with your sine and cosine functions because they kind of repeat over time. And again, we just don't know what's happening near 0 because of how quickly it's oscillating near 0. Okay, so that just happens. All right, so hopefully this helped you out. Again, we did it numerically and graphically. Understanding them both numerically and graphically are very, very, very important to get to the next stage. Okay, so hopefully this helped. Again, if you want to use Desmos calculator for the table, I would, highly recommend that. Again, in class, especially when you take your AP exams next year, if you're juniors, or if you're sitting in Calc 1 next year in the classroom at college, you may not have Desmos as your access, so kind of get used to using the graphing calculator or your normal calculator so that you can plug these in. Again, this calculus is very fun for me. So we're going to get into some heavy lifting, especially next week. But again, hopefully I introduced this very well. It's my first time doing it. You are the first class to hear me teach a little bit of calculus, and I'm very excited for it if you can't hear it now. But again, hopefully you guys do well. Enjoy this. I'm very excited for what's to come in the following weeks. All right, so hopefully this works out for you guys. Thank you for listening.